In this session, we'll be talking about continuous probability distribution. Just like the way we have spent about discrete probability distribution, where we have focused on the uniform distribution, the Bernoulli distribution, the binomial, negative binomial, geometric, hypergeometric, and Poisson distribution. Just like the way we have spent trying to understand all these distributions, which are all discrete. Now our focus will change to continuous probability distribution, wherein again in the continuous case also we do have a uniform distribution. Then I'll be talking about gamma distribution, which is one of the most important of the continuous distributions. Then we will discuss about the exponential distribution, which has some kind of relationship with the gamma distribution. Similarly, we will talk about the chi-square distribution. So these three can be derived. So if I say gamma is like a parent distribution, exponential and chi-square distribution are some kind of special cases of the gamma distribution. So let's try to understand that aspect. And we would also spend some time trying to understand the beta distribution as well. And of course, the normal distribution, one of the most important of the distributions in terms of the continuous case. So we will spend some time in terms of understanding the normal distribution and how can normal distribution be approximated from the discrete distribution, especially the binomial distribution. How can binomial distribution be converted into a normal distribution? In what cases binomial distribution can be approximated to a normal distribution? These are the different areas that we are looking at in this session. So getting forward, trying to understand first the uniform distribution. So these are all continuous distributions. We had a uniform distribution under the discrete case as well. But what we are looking at here is the continuous case of the uniform distribution. So the uniform distribution will have two important parameters, alpha and beta, which talk about the range, right? So here if you see, alpha and beta are the range of values. What it says is the uniform distribution with the range of alpha and beta. What we typically see is the probability density will be equal to 1 by beta minus alpha. So almost it's a constant, right? Because beta is the constant, alpha is the constant, 1 by beta minus alpha is the constant for x lying between alpha and beta. So the probability density function f of x should be more like this. It should be equal to 1 by beta minus alpha, two constants, as long as x is lying between alpha and beta, and it should be 0 everywhere else. So that kind of distribution is what we are calling as a uniform distribution. In the discrete case also we had a uniform distribution which said the probability distribution function should be equal to 1 by k for all the k different values which the random variable can take, and it should be 0 elsewhere. So it is more like it's a constant. All of them have equal probability. The same logic goes even in case of continuous. The probability is 1 by beta minus alpha as long as the x is lying between alpha and beta, and it is 0 everywhere else. Now coming to some important computations associated with the uniform distribution. If I know that my data is uniformly distributed between alpha and beta, right, the probability density function being 1 by beta minus alpha, a few more important computations can be done quite quickly. One being the mean of that uniform distribution. works out as the average of alpha and beta, which is alpha plus beta by 2. And the variance of such kind of uniform distribution comes out as 1 by 12 times beta minus alpha whole square. So that is working out as the second moment, right? The second central moment, which works out as 1 by 12 into beta minus alpha whole squared. So the variance is coming out through this formula, and the mean is coming out through this formula. You can very well use the expected value of x formula, wherein you are trying to do the integration between x and f of x, product of x and f of x dx. Based on that, and after that, once you have got your expected value, so this should be your expected value, which is alpha plus beta by 2. Right, you can very well see that the constant, this is 1 by beta minus alpha, f of x is 1 by beta minus alpha, so x into this, right? If you see here, you are integrating it between alpha and beta, x into f of x dx. So you are integrating between alpha and beta, x into f of x is 1 by beta minus alpha dx. So I'll take out 1 by beta minus alpha. So the integral of x is x squared by 2, integrated between beta and alpha makes it 1 by beta minus alpha, beta squared minus alpha squared by 2. So beta minus alpha, it goes as beta plus alpha by 2. So expected value of x is alpha plus beta by 2. Then similarly, I can find out expected value of x squared the same way, integrating between alpha and beta, x squared times f of x. So I'll take 1 by beta minus alpha outside dx. So which is nothing but x cubed by 3, right? You integrate it between beta and alpha, 1 by beta minus alpha. So which works out as beta cube minus alpha cube divided by 3 into beta minus alpha, which again in turn works as, right, this beta cube minus alpha cube, a cube minus b cube, a minus b into a squared plus ab plus b squared. So which becomes beta squared plus alpha beta plus alpha squared divided by 3. So this is the expected value of x squared. So I can very well find out now the variance of x, which is nothing but expected value of x squared minus expected value of x whole squared, alpha plus beta whole squared by 4. So overall, if you look at here, 3/4, 4 beta squared plus 4 alpha beta plus 4 alpha squared minus 3 alpha squared minus 6 alpha beta minus 3 beta squared. Now if I simplify it, this is beta squared minus 2 alpha beta plus alpha squared by 12, which is nothing but alpha plus alpha minus beta whole squared by 12. So the variance can be computed this way. So I can very well, once I know the probability density function, and I also know I can do the integration comfortably, then I'm able to find out the mean variance associated with any of the distribution. So this is how we can derive the same for the uniform distribution. Alright. Then the next important distribution that I am discussing in this context is the gamma distribution, wherein here we are talking about a family of distributions first. The family of the distributions is, if they are of this form, some constant times x to the power of alpha minus 1 and e to the power of minus x by beta. If this is the kind of a density function I am coming across, right, for different values of alpha and beta. So here the parameters are alpha and beta. But if I can get a density function of this form where we are talking of 1x which is raised to some power and another x which is a power of e power, right, which is an exponent of something. So if you have some such kind of a function where we are talking about some constant times x to the power of alpha minus 1 e to the power of minus x by beta for x is greater than 0 and it is 0 elsewhere. So if you have such kind of family of distribution, if you are finding the density function which is of this form where both alpha and beta are positive, and this kind of family of distributions come under the gamma distribution. So one way to remember the gamma distribution is x is raised to some power, right? The data is the variable is raised to some power alpha minus 1, and at the same time exponent e is raised to the power of minus x by b. So we have one portion of the observations as a base, and there is one more portion of it as a power of the e power, as a power of e, and the k has to be evaluated in such a way that the area under the total curve, whatever is this curve, this is the curve, the area under the total curve should come out to be 1, and that's how the k is typically chosen. So I can very well substitute y equal to x by beta. If you say this whole thing is y, then what is happening? Integration now, because I know that the overall integral minus infinity to plus infinity f of x dx should be equal to 1, right? Minus infinity to infinity f of x dx should be equal to 1. Now the same logic, because the total probability should be equal to 1. So this whole thing I integrate it between 0 to infinity, because I don't need to minus infinity to infinity because x is only positive. So I am taking an integral between 0 to infinity k x to the power alpha minus 1 into e to the power of minus x by beta dx. So I am taking out k, because I have substituted y equal to x by beta, right? So x will become beta y. So dx I will replace it with beta dy. Dx will be replaced with beta dy. And now I can very well now, instead of saying e to the power of minus, so wherever I have x, right, I have to write it in form of y. So x is beta y, right? So this is where I will write, instead of kx to the power of alpha minus 1, I will write it as k beta to the power of alpha minus 1 and y to the power of alpha minus 1 and e to the power of minus x by b. So e to the power of minus y, dx is nothing but beta dy. So the overall thing is coming out as k into, so there are two betas here, beta to the power alpha, y to the power alpha minus 1, e to the power of minus y dy. So this is a constant part, so I'll take this out, k beta to the power alpha. I'm integrating this between 0 to infinity, y to the power alpha minus 1 e to the power of minus y dy. So this is what we call as a gamma function. This is what we call as a gamma function, y to the power of alpha minus 1. So for some kind of an alpha, for any particular value of alpha, when I say gamma function, it is nothing but y to the power of alpha minus 1 e to the power of minus y integrated over the entire values of alpha, over all values of y. But of course alpha needs to be positive here. Now, the simplification here, right? Probably I can do an integration by parts. If you do the integration by parts, it goes more and more recursive, right? Because here we have y to the power of alpha minus 1 and e to the power of minus y. So you can very well use your UV rule to do the integration till the last, right? You can take the differentiation of this alpha minus, so you can take the integration here, you can take the differentiation of this, and you can use the multiplication rule of probability to simplify this integral. But what you will finally arrive at is a recursive kind of a formula which comes out as gamma of alpha, right? Gamma of alpha, which comes out as alpha minus 1 times gamma of alpha minus 1. So this keeps going. Now again, gamma of alpha minus 1 will go as alpha minus 2 times gamma of alpha minus 2. So you could see here it is coming out as a recursive alpha minus 1 into alpha minus 2 into alpha minus 3 so on, which will actually become alpha minus 1 factorial, especially when alpha is a positive integer. Right, I can very well take it as a positive. If I take alpha to be a positive integer, this entire gamma value, which is nothing but y to the power of alpha minus 1 e to the power of minus y integrated between 0 and infinity, if I try to do the product multiplication formula of integration by parts, I can very well solve this and I'll finally get gamma of alpha is nothing but alpha minus 1 factorial, especially when alpha is a positive integer. So wherever you are finding alpha to be a positive integer, the gamma of alpha directly comes out as alpha minus 1 factorial. And in some cases, there is also one more way of understanding the same. Gamma of half. There is one more such kind of a formula. Gamma of half is nothing but square root of pi. So that's one more special value where you can very well take gamma of half is again it works out as y to the power of minus half e to the power of minus y dy. So again, if we try finding out the gamma of half, it works out to be square root of pi. So that's also one more special result which we can use for a lot of problem solving. Now based on this, you could see that you can find out the value of k now, because I'm coming back to this. This whole thing we are saying, okay, when I'm integrating this whole part, right? So when you are integrating this 0 to infinity, y to the power of alpha minus 1 e to the power of minus y, which works out as this whole thing is working out as gamma of alpha. This whole thing is coming out to gamma of alpha. So k beta per alpha gamma of alpha, this is equal to 1. So from here you are able to make out that the k is nothing but 1 by beta to the power alpha gamma of alpha. So that's a typical formula, so which means the gamma distribution function is nothing but if any probability density is of this form 1 by beta to the power alpha gamma of alpha, and gamma of alpha I have already specified that it is alpha minus 1 factorial x to the power alpha minus 1 e to the power of minus x by beta. If you find any probability distribution or density function of this particular form, then that is what we are calling as a gamma distribution. For different values of alphas and betas, we get different kinds of distributions. If you see here, if alpha is half, beta is 1, this is the kind of a distribution that you are going to get. Right, this is the kind of a shape that we are getting for different values of x. Similarly, if alpha equal to 2, beta equal to half, we get this kind of a graph. If alpha equal to 1, beta equal to 1 by 5, we get this kind of a graph. So for different values of alpha and beta, you can very well check what is the kind of a graph that you are able to generate. You can take different values of x. So if I really want to showcase this, let me take different values of x from 0 to 5, right, just to demonstrate this. So let me take x is 0, 1, no sorry, let me take it in small intervals so that the graph can be made very comfortably. I'll take 0, 0.1, 0.2, so on. Let's say, let me take the values up to 5 or 6, right? So these are the different values of x. Now I will take alpha equal to half, beta equal to 1. Right, beta, let me take it as 1. Now I can very well find out the probability density function f of x. In this case, it is nothing but 1 by beta to the power alpha. So let me find this out. 1 by, I have to take it as beta to the power alpha, beta to the power alpha, right, multiplied by gamma of alpha. Here gamma of alpha, because alpha is 0.5, I cannot, right, gamma, okay, gamma of alpha. Alpha is this one, gamma of alpha. So this is the denominator part. Then in the numerator I am taking x to the power of alpha minus 1. So x is this one to the power of alpha minus 1. This is alpha minus 1 into e to the power of minus x by beta. E to the power of minus x divided by beta. So this is the kind of graph that I am trying to talk of. For x greater than 0, so for greater than or equal to, it does not work. So for 0, you forget about it. But for x greater than 0, this is the kind of a shape that I am getting. Probably let me remove this altogether. Right, I can very well delete this part. So I am getting for x is 0, 0.1, 0.2, so on. Now when I am trying to draw this graph, I could see that if I draw a simple line chart, the kind of graph that I am getting is more like this. And this is what is the shape here, which is what is coming out as an exponential distribution. But now change alpha equal to 2, beta equal to half, alpha equal to 2, beta equal to half. Now this is the kind of a graph that I am getting when alpha equal to 2, beta equal to half for the same kind of a data. And similarly, if I am making alpha equal to 1, beta equal to 1 by 5, alpha equal to 1, beta equal to 1 by 5 is 0.2. So for different values of alpha and beta, I am getting a kind of different kinds of shapes, right? Alpha equal to 1, here they have made alpha equal to 11. So alpha equal to 11, so which is working out more like this. So for different values of alpha and beta, we are getting different kinds of graphs altogether. So this is what is the gamma distribution. So where I am talking about a density function of the kind 1 by beta to the power alpha, gamma of alpha multiplied by x to the power of alpha minus 1 e to the power of minus x by beta. Right? So this should be the probability density function. Alpha, beta, both of them are greater than 0. Now, in case of gamma distribution, a few important functions to be comfortable with. a few important distributions, a few important calculations regarding the gamma distribution is we are talking about the rth moment. Rth moment about the origin is given by beta to the power r gamma alpha plus r divided by gamma of alpha. Probably you could quickly check it out, right? If you are looking at rth moment about the origin, I can very well take it as x to the power r because I am finding out the rth moment about the origin. I am integrating it between 0 to infinity, x to the power of r into f of x dx. F of x is already known, 1 by beta to the power alpha gamma of alpha. Then I have x to the power of alpha minus 1 e to the power of minus x by beta. So this is what is my rth moment. So I'll take out from this, I can very well take out the gamma of alpha, I can take out. So x is becoming x to the power of, because I am multiplying it with r, it is becoming x to the power of, so I'll take out gamma of alpha outside, right? When I am taking 1 by gamma of alpha outside, it is becoming e to the power x to the power of r plus alpha minus 1 divided by beta to the power alpha, and this is e to the power of minus x by beta dx. So I'll multiply both the numerator and the denominator by beta to the power r. So this becomes 2 beta power r. Here it becomes beta to the power alpha plus r. So just by multiplying numerator and the denominator by beta power r. Now you could see here, now probably the new alpha for me is r plus alpha. Alpha 1 you call it as r plus alpha. So replace this by alpha 1, replace this by alpha 1. Now what is that you are finding here? X to the power of alpha 1 minus 1. Let's look at this part. X to the power of alpha 1 minus 1 and e to the power of minus x by beta and divided by beta to the power alpha 1. Now this entire thing is nothing but gamma of alpha plus r, right? This is coming out as gamma of alpha plus r. If you see here, x to the gamma function, x to the power alpha minus 1 by beta to the power alpha and e to the power of minus x by beta. If you are looking at this whole thing, this is what we called as the beta function, the gamma function. So this would become gamma of x plus alpha plus r. So this whole thing is becoming beta to the power r gamma of alpha plus r divided by gamma of alpha. So that is what we are getting as the rth moment about the origin. And if I am substituting even from here, I can very well substitute r equal to 1 where I get my first moment. So when I substitute r equal to 1, this becomes beta, right? To get the mean, I can substitute r equal to 1 because the first moment is nothing but the mean. Gamma of alpha plus 1 divided by gamma of alpha. And we know that alpha plus 1 is nothing but alpha plus 1 into gamma of alpha. So here it is alpha into gamma of alpha. So I'll get this off, which will make it alpha beta. So the mean is alpha beta here. Similarly, I can use the same formula to find out the second moment, which is expected value of x squared, by substituting r equal to 2. So which becomes beta squared gamma of alpha plus 2 divided by gamma of alpha. Gamma of alpha plus 2, I can write it as alpha plus 1 into alpha into gamma of alpha. So once I take this out, it becomes beta squared times alpha into alpha plus 1. This is what is expected value of x squared. So if I want my variance, it is nothing but expected value of x squared minus expected value of x whole squared. Expected value of x whole squared is nothing but alpha squared beta squared. So if you go ahead and simplify, alpha squared beta squared plus alpha beta squared minus alpha squared beta squared will give me alpha beta squared, saying that the variance of the gamma distribution is alpha beta squared. And you also have another important formula to look at here, the moment generating function associated with the moment generating function associated with the gamma distribution is 1 minus beta t to the power minus alpha. Because if you try differentiating this, because you can find the moments by differentiating this and putting t equal to 0. So I am differentiating this with respect to t. So t to the power of n kind of 1. So which is minus alpha into 1 minus beta t to the power minus alpha minus 1. And integrating this part inside, it is minus beta. So I will make this as plus, make it alpha beta. When I substitute t equal to 0, so this whole thing, this is 0, which is making it 1 to the power something, 1 multiplied by alpha beta is giving me that my mean is alpha beta. The same way I can find out the second derivative and then substitute 0 for t in the second derivative to get my expected value of x squared. Then again for variance, I can very well subtract expected value of x squared minus expected value of x whole squared to arrive at the variance of the gamma distribution. So some of the important points for you to work out with respect to the gamma distribution. Alright. Then the next aspect that we have to look at once we get a clarity on gamma distribution is a special case of gamma distribution, which is called as exponential distribution. So especially when your alpha is 1 and beta is some theta, then we say that the gamma distribution will become an exponential distribution. If we simply see that 1 by, for gamma distribution we said 1 by beta to the power alpha gamma of alpha and x to the power of alpha minus 1 e to the power of minus x by beta. This is what we said in case of a gamma distribution. Now just try substituting alpha equal to 1, beta equal to some theta. So alpha equal to 1, so it is 1 by theta. Gamma of alpha is gamma of 1. Gamma of 1 is 0 factorial, which is 1. Then we have x to the power of alpha minus 1. Alpha is 1, so 1 minus 1 is 0. So this will, x to the power of 0 is again 1. E to the power of minus x by beta is nothing but minus x by theta. So overall it is working out as 1 by theta e to the power of minus x by theta. So if the probability probability density function is of this form, which is a simplified version of a gamma distribution where alpha equal to 1. So this kind of a distribution is what we are calling as an exponential distribution. A special case of a gamma distribution when alpha equal to 1 and beta equal to theta. And coming to the practical usage of exponential distribution, it is determining the probability density of the waiting time right? We are talking about getting a first success. You are repeating the experiment so many times. We are getting a first success. We are talking about the waiting time until the first success, or even waiting time until between two successes. So if I have to really model that particular aspect, I want to find the waiting time between the successes or to the first success. There's a very important application of exponential distribution. So just look at this. Consider the probability of getting X successes in a particular time period. Right? During a particular period of time, let's say within a day, I'm talking about getting X number of successes. And the way it is considered is probability of success during very small time interval from t to delta t during this period. I'm talking about the probability of success being proportional to the time period. So alpha times some delta t. Right? This is what we are calling as a Poisson process. We are talking about probability of getting X successes during a time period t. So during the whole time period t, we are thinking of getting X number of successes. During a very small time interval t to t plus delta t, kind of a very small interval, during that period the probability of success is some alpha times the time period, proportional to the time period, and probability of more than one success during this period is very negligible. And if the success will come during this period or not is completely independent of the success occurring during this period. Success occurring during this period has nothing to do with the success occurring in the previous two periods. They are completely independent. Success during a very small time interval does not depend on what has happened in the previous time period. When all these things are typically satisfied, we call that kind of a process as a Poisson process. And in this Poisson process, if I want to find out the expected waiting time to get a particular success, I can very well call it as an exponential distribution. Probably here you could see the reason why. So if I'm talking about number of successes, right, during the entire time period, which is what we said, we get X successes. So number of successes, which is X, is having a Poisson distribution with lambda alpha t, because alpha is the alpha is the probability of success within a very small time interval, and I have t such kind of time intervals. So within a total time period of t, the probability of getting success is alpha t. So we are putting lambda is we are taking the lambda as alpha t. Now if I want to find out what is the probability that I get y or lesser number of successes, so which is more like 1 minus of probability of y greater than y, getting more number of successes than y. So I am trying to find out 1 minus of p of 0 successes in a time interval. So the time interval that is taken to get the first success is more than y. So I want to see if there are 0 successes in a time interval of length y. I am subtracting that part. So because I am talking about 0 successes, right, I'm thinking of at least getting X success. So that's where I'm talking about 0, getting the first success. I want to find the time until I get the first success. So which is nothing but the probability of getting 0 successes I am subtracting, so that I am getting my first success. So what is the probability of 0 successes if I am very much finding out the Poisson distribution? E to the power of minus lambda, lambda to the power x by x factorial, which is nothing but e to the power of minus alpha t. So this is the probability of getting 0 successes. Now at least the first success, the probability of getting is 1 minus e to the power of minus alpha t. At least one or more kind of successes. So that is where we get f of y is 1 minus e to the power of alpha y. Now I can, so this is the distribution function. I can very well take the differentiation of it to get the density function, and the differentiation of this is coming out as f of y alpha e to the power of minus y, because this, if I take a derivative, alpha e to the power of minus alpha y. So this is the density function associated with the exponential distribution. So if we have a Poisson process, I can very well compute the waiting time until the first success. Right, we have seen here. So we are talking about the some kind of a success. So I am subtracting probability of 0 successes from the overall probability of 1, which is saying that the time period is lesser than this much in terms of getting the first success. So this is how the distribution of the waiting times in terms of getting the success lies with respect to the exponential distribution, which works out as alpha into e to the power of minus alpha y, and it is 0 elsewhere. And the other way these things are linked up is theta. In this case, if we are talking about the distribution here, you can very well take theta as 1 by alpha. If I have to equate these two things, theta is coming out as 1 by alpha. So that's the parameter that is associated with the exponential distribution. So exponential distribution with theta equal to 1 by alpha. You can also use the same formula for computing the waiting time between any number of successes, between the second and the third success, fifth and the sixth success, because they are all independent. So just like the way we have computed the value associated with the first success, we can repeat the same thing with respect to any kind of between any two successes as well. Let's look at a quick example here. At a certain location on a highway, the number of cars exceeding the speed limit by more than 10 miles per hour in half an hour is a random variable having a Poisson distribution of lambda equal to 8.4. What is the probability of a waiting time of less than 5 minutes between the cars? So in a half an hour time, I am able to find 8.4 on an average, 8.4 cars exceeding 10 miles. So I am talking about what is the probability of waiting time of less than 5 minutes between the car exceeding the speed limit by more than 10 miles per hour. So because here I am having half an hour as the unit of time, because it is 8.4 per half an hour, right? So 8.4 is per half an hour. So I am taking lambda is 8.4, and I am talking about the waiting time exponential distribution with theta. Theta I will have to take it as 1 by lambda or 1 by alpha. So which is working out as 1 by 8.4. That is what is the theta I will have to take here, because in case of Poisson distribution, whatever is the lambda, in case of exponential distribution, it becomes reciprocal for theta. And if I am talking about the waiting time being less than 5 minutes, so I am measuring in terms of half an hour. So what is the probability that x is less than 1 by 6? Because 5 minutes as a unit of half an hour, it is 1 by 6. So all I really want is the probability that x lies between 0 to 1 by 6. Then I have to mention it as 1 by theta e to the power of minus theta minus x theta. So which is minus x by theta. That is or probably you can have it as alpha e to the power of minus alpha y. Alpha is 8.4 e to the power of minus 8.4 x dx. So you could very well do the integration of this 8.4 e to the power of minus 8.4 x divided by minus 8.4. These two are integrated between 1 by 6 and 0, right? So which is working out as e to the power of minus 1.4 minus e to the power of 0, 1. It comes out as 1 minus e to the power of minus 1.4. I can very well find out what is the probability that there is less than 5 minutes of waiting time, that the speed is exceeding by more than 10 miles per hour. So this is the way we can solve the probability examples with respect to the exponential distribution. And corresponding to this exponential distribution, we have the mean, which is equal to theta, which is nothing but 1 by lambda, and variance comes out as theta square. Those are the numbers. Probably you can quickly check. If we are talking about the distribution function, the density function, 1 by theta e to the power of minus x by theta, right? So f of x is 1 by theta e to the power of minus x by theta. And if I want to find out the mean, I am very well multiplying this by x and dividing this whole thing between 0 to infinity. So I can take out 1 by theta, and I am doing the integration between x e to the power of minus x by theta. So I can very well do an integration by parts here. So x, so when I am doing integration by parts, I am talking of x. I am taking the integration of e to the power of minus x by theta divided by minus 1 by theta, which becomes minus theta here, right? And minus the differentiation of x, I am doing it by parts. So the integration of the differentiation of this, which is 1, and the integration of this is becoming minus x by theta divided by minus 1 by theta. So basically it becomes plus theta times dx. So this part is already integrated. Minus theta x e to the power of minus x theta. This I can very well integrate it between infinity and 0. So the infinity part is e to the power of minus infinity is coming out to be 0. So this part is eliminated, 0. E to the power of 0 is 1. Multiplied by 0, again this part is also 0. So this part can very well be omitted for computation of the mean. Then here it is theta times integration of e to the power of minus x by theta d theta. So which I can very well get minus x by theta divided by 1 by theta. So this is coming out as theta squared, and I have 1 by theta outside. So I have 1 by theta outside, this is theta squared, and this I am integrating it between infinity and 0. E to the power of minus infinity is 0, e to the power of 0 is 1. So this becomes 1 by theta into theta squared, which will get solved as theta. So the mean of it comes out as theta. The variance of it, again you can very well try the same thing. You can get your expected value of x squared, which you have to integrate by parts 3 times, right? Because x squared, x and a constant, and based on that you can very well compute the variance. You will get your expected value of x squared. From there you can compute the variance as expected value of x squared minus expected value of x whole square. Then now that we got another hold on the exponential distribution, which is again a special case of a gamma distribution, we will look at another distribution which is also a special case of gamma distribution, which is the chi-square distribution, where alpha is some nu by 2 and beta is half. When I am having alpha is some nu by 2 and beta is 2, this gets converted the chi-square distribute the gamma distribution gets converted into a chi-square distribution with new degrees of freedom. The same, whatever it is, the gamma distribution gets converted into a chi-square distribution with new degrees of freedom. So which is always like, where gamma distribution is 1 by beta to the power alpha gamma of alpha, and then we had x to the power of alpha minus 1 e to the power of minus x by beta. Now wherever beta is there, I'll take it as 2, right? Wherever beta is there, I'm taking it as 2. Wherever alpha is there, I can take it as nu by 2. So that is what is this expression that is coming out. So wherever you have this kind of relationship, which is also a family of a gamma distribution, which is the chi-square distribution. So when we have alpha equal to this much and beta equal to 2, we can very well say that this particular distribution will get converged to a chi-square distribution. Now for this distribution also we can very well find out the mean and the variance. Mean is nothing but nu, right? If you look at your gamma distribution, we said you go back to the gamma distribution. In the gamma distribution, we have simply called the mean is alpha beta and variance is alpha beta squared. Just try it out here, right? Alpha beta, the same thing, 1 if you remember. Now if you see here, with respect to the gamma distribution, if I apply the same, alpha is nu by 2, beta is 2. So the mean will become nu. Alpha is nu by 2, beta is 2, 2 squared is 4. So variance will become 2 nu. So you can apply the same alpha beta squared. Even in case of exponential distribution, you can try the same. Right, we have already said here alpha equal to 1, beta equal to theta, right? So alpha beta is the mean, alpha equal to 1, beta equal to theta, so this becomes theta. Alpha beta squared, alpha equal to 1, beta equal to theta, so variance is theta squared. So you can very well substitute that special cases also to arrive at your chi-square distribution, mean, variance, everything associated with the chi-square distribution. So a lot of things associated with the chi-square distribution can very well be derived from the original gamma distribution itself. So that makes things more and more easier as well, right? Now let's discuss the next distribution, which is the beta distribution. So here the general form of the beta distribution for a probability density function, x to the power of alpha minus 1, this was there even for gamma, but in gamma we had it as e to the power of minus x by beta. So x is there as a part of the power there, whereas here we are having it again in the base 1 minus x to the power beta minus 1. So when we have x and 1 minus x, more or less similar to your binomial distribution with small variations, but that binomial is for a discrete case. Here we are talking about beta distribution for a continuous case, and here the alpha and beta may not be related to each other. Right, there we talked about n trials, x successes, n minus x failures. But here the alpha and beta are two different parameters associated with this distribution. So whenever we are seeing a probability density function of this form, x to the power of alpha minus 1 and 1 minus x to the power of beta minus 1 and multiplied by gamma of alpha plus beta divided by gamma of alpha into gamma of beta, then we call this kind of distribution as a beta distribution. A few more important points here. The x has to be between 0 and 1 only. In case of gamma distribution, we had x Greater than 0, that's it. We didn't have any such kind of a restriction that it has to be between 0 and 1. So, but alpha and beta are positive numbers, just like in case of gamma distribution. Now, what we also have to understand is, again, from the beta distribution, again, a few more distributions can be derived. One is the uniform distribution, the continuous uniform distribution, where you are saying f of x is 1 for alpha is for x lying between 0 to 1. So when you are saying f of x equal to 1 for the entire thing lying between 0 and 1, in that case where you are getting alpha equal to 1, beta equal to 1. When you have alpha equal to 1, beta equal to 1, this is becoming 0, this is also becoming 0. So when both of these are becoming 0 and it is between gamma of 2 divided by gamma of 1 into gamma of 1. Gamma of 1 is also 1, this is 1, this is also 1. So all of them, because gamma of 1 is 1, gamma of 2 is 1 factorial, gamma of 1 is 0 factorial, all of them are 1. So the whole thing will become f of x equal to 1. Now in that case we are talking about a uniform distribution. So that is where uniform distribution is a special case of beta distribution when alpha equal to 1 and beta equal to 5. Today we are seeing lot many applications of beta distribution in the Bayesian inference, in the Bayesian probability computations. We see lots and lots of beta distribution applications where we use the terms like prior distribution. Based on the likelihood, we talk about the posterior distribution that is more or less looked at from the perspective of the beta distribution itself. So now that this is the probability density function, it means that if I am integrating this over 0 to 1, the overall probability should be, the integrated value should be equal to 1, right? So I can very well say gamma of alpha plus beta divided by gamma of alpha times gamma of beta, x power alpha minus 1, 1 minus x to the power beta minus 1 dx. So this entire thing should be equal to 1. So from here I can very well take only the integral 0 to 1 x to the power alpha minus 1, 1 minus x to the power beta minus 1 dx. This should be equal to gamma of alpha into gamma of beta divided by gamma of alpha plus beta. So this is what we typically call as the beta function. The beta function or the beta function, it takes two parameters alpha and beta, right? So this particular integral where I am talking of x power alpha minus 1 into 1 minus x power beta minus 1, I can call this as the beta function with alpha and beta as the parameters, and this can be computed using alpha gamma of this whole integral. I can very well compute using gamma of alpha times gamma of beta divided by gamma of alpha plus beta. So that's one more important point that you need to be comfortable with. Then we are talking about the computation of the mean and the variance associated with this beta distribution, right? So if I have to compute the mean, so here I am setting this entire thing, which I'll take out gamma of alpha plus beta by gamma of alpha into gamma of beta, integrating it between 0 to 1, x times x to the power alpha minus 1, 1 minus x to the power beta minus 1 dx, right? So I can very well take this. Now this is x to the power of alpha, right? This is becoming x to the power of alpha. So because this is x to the power of alpha, I can very well take this, okay? I can very well take this as alpha plus 1 minus 1. Can I take it like this? If I take alpha plus 1 minus 1, it becomes x to the power of alpha only. So it is becoming, if I'm looking at this whole integration, right, this is becoming gamma of alpha plus 1 into gamma of beta divided by gamma of alpha plus beta plus 1. Now we have already said this is nothing but alpha plus beta times gamma of alpha plus beta. So these two go off, and this gamma of beta is going off. This I'll call it as alpha times gamma of alpha. So even these are going off. So finally I'm left with alpha by alpha plus beta. So this is how I'm getting my mean. So the mean of this beta distribution is alpha by alpha plus beta. The same logic I can go to compute my expected value of x square. Right? I can very well take gamma of alpha plus beta divided by gamma of alpha times gamma of beta multiplied by 0 to 1 x squared times x to the power alpha minus 1 1 minus x to the power beta minus 1. So because this is alpha plus 1, I can write it as alpha plus 2 minus 1. So that's the reason this will become gamma of alpha plus beta divided by gamma of alpha into gamma of beta. Now the alpha will become alpha plus 2. Right? Then it would become a beta function directly. So that's where this will become gamma of alpha plus 2 gamma of beta divided by gamma of alpha plus 2 plus beta. So this will become, if I am striking these two things off, this is alpha plus beta plus 1 into alpha plus beta, whereas these two will go out directly, and this will become alpha plus 1 into alpha. So this will be my expected value of x squared. Alpha plus 1 into alpha divided by alpha plus beta into alpha plus beta plus 1. Right? So that is expected value of x squared. So from here I can find out my sigma squared, which is alpha into alpha plus 1 expected value of x squared, alpha plus beta into alpha plus beta plus 1. This is the expected value of x squared minus expected value of x whole square, which is alpha squared by alpha plus beta squared. So that's where I will get it as alpha plus beta squared into alpha plus beta plus 1. This is what I'll get as an LCM. So alpha plus beta into this. So this becomes alpha into alpha plus 1 into alpha plus beta minus alpha squared into alpha plus beta plus 1. So which will become the numerator wise, now if you see, alpha cube alpha beta plus alpha squared beta, right, plus alpha squared plus alpha beta, that's the first part, minus alpha cube minus alpha squared beta minus alpha squared. This is what is the numerator. Denominator is alpha plus beta squared into alpha plus beta plus 1. Striking off alpha cube, striking off alpha squared beta, striking off alpha squared. So what I am left with is alpha beta by alpha plus beta whole squared times alpha plus beta plus 1. So this is the typical variance associated with the beta distribution. So you'll get the mean value, you have the variance, you can very well use these numbers to calculate the for any kind of a numerical that you come across. Alright. Now that's what you need to understand regarding the beta distribution. Now let's move on to the next concept, which is the normal distribution. Probably one of the most heavily useful distributions in the entire modern statistical theory. So it's a bell-shaped distribution. It is defined by two parameters called mu and sigma, wherein the density function comes out as 1 by sigma root 2 pi e to the power of minus half x minus mu by sigma whole square. That's the probability density function associated with the normal distribution. And one specific aspect of the normal distribution here is the x value can range anywhere between minus infinity to infinity, right? So that is one important thing that we are considering here. X could be anything between minus infinity to infinity. The sigma will always be a positive quantity here, right? I think sigma did not come out here. Sigma is a positive quantity always. So parameter of mu, if you look at the way you are getting the mu, which is the parameter out here, is nothing but the expected value of x. Whereas when you are getting the parameter sigma, it is nothing but you are getting the square root of the variance of x. So that's one of the another important aspects associated with a normal distribution. The parameters of the distribution itself, the mu and sigma, those are nothing but the mean and the standard deviation associated with the distribution itself. The total area under the curve, the normal curve, the total area underneath it should be 1. This is the case for any kind of a distribution, right? I'll have the total area under the curve equal to 1. But if I have to quickly look at that, I'm taking the integration minus infinity to infinity, right? 1 by sigma root 2 pi e to the power of minus half x minus mu by sigma whole squared dx. Now here I'm taking one quick substitution z, right? I'm taking one quick substitution z, which is x minus mu by sigma. So from here, because mu and sigma are constants, dz will come out as dx. So I can directly take the step. Now because zx is from minus infinity to infinity, even this would be from minus infinity to infinity. 1 by sigma root 2 pi e to the power of minus half z square dz, right? So I can take out 1 by root 2 pi e to the power of minus half z square, right? So I am taking out 1 by root 2 pi, again minus infinity to infinity, 1 by sigma e to the power of minus half. Oh, okay. Here dz is dx by sigma, right? Because the addition will not have an impact on the z, but this is a multiplication. So dz will be dx by sigma. So the whole of dx by sigma, I'll take it as dz e to the power of minus half. So this I'll take it as only 1 by root 2 pi e to the power of minus half z square dz, right? Now when I'm taking, I can very well break this out minus infinity to infinity, because this is an even function. I can very well take it as half of it. So I'll take the double of it here and say 0 to sigma, because I'll take the minus as well as plus. I'll put 0 to this one e to the power of minus half z square, because it's a even function, symmetric. So that's where I'm considering 0 to sigma e to the power of minus half z square dz. And if you really look at this part, gamma of half, if you try out gamma of half, how much is gamma of half? If you are expressing it in the integral form, gamma of half is integral 0 to infinite. So if we have defined the gamma function, right? The way we have defined the gamma function, if you try to recollect, it is y to the power of alpha minus 1 e to the power of minus y dy. That is what we call as the gamma function. Now, going with the same concept here, e to the power of minus half z square, and you set alpha equal to alpha equal to 1, sorry, alpha equal to half. If you set alpha equal to half, this is what is becoming 0 to infinite y to the power of minus half e to the power of minus so write it like this, e to the power of minus half z square, right? For the gamma function, this is what is gamma of alpha, right? So try expressing it that way. So where I can equate this part. So I'll take half z square is equal to y. So z square equal to 2y, 2z dz equal to dy. So based on this, I'll get dz is nothing but 1 by 2z times dy. So here I'll make it as 2 by root 2 pi. This I'll take it integral between 0 to infinity. E to the power of minus half z square, I'll make it as e to the power of minus y. And in place of dz, I'll take it as 1 by 2z dy. So this I'm taking it out, making it z to the power of minus 1. So z again, if I have to convert it in terms 1 by z, this is right. So 1 by z, we have already made 1 by 2 z square is y. So from here we are getting z square equal to 2y. Z should come out as square root of 2y. So this is where now I can't directly take it out because z comes out as square root of 2y. So the whole thing will come out as 1 by root 2 pi into integral of 0 to infinite e to the power of minus y and 1 by root 2y. So I am again bringing out one more root 2 outside. Right, I am taking out a root 2 outside. Z I'll write it as root y. So which is nothing but y to the power of minus half. So dy. Now I can very well take alpha equal to half, wherein this entire thing is becoming equivalent to gamma of half. So I can write this as gamma of half divided by square root of 2. And we have already defined gamma of half is square root of pi divided by square root of 2. So this whole thing is coming out as square root of pi by square root of 2. We already have got 2 by square root of 2 pi here. So I'll take it as square root of pi by square root of 2. Overall is working out to exactly equal to 1. So the area under the curve for a normal distribution is working out to 1. So wherein I have taken the help of a gamma as a function. So that's the way we can simplify this altogether. Then a few other important points in this context. Right, we got the probability distribution function, everything. Area under the curve, we are able to show it as 1. Then we have a moment generating function e to the power of mu t plus half sigma squared t squared. Right, if you really want to look at the moment generating function for this, we can very well look at it right? Because we are talking about e to the power expected value of e to the power of tx. So e to the power of tx, multiply it with 1 by sigma root 2 pi the f of x, e to the power of minus half x minus mu by sigma whole square. So this is what has come out. So from here the constant term I'll take out first to avoid the confusion. I'll take out 1 by sigma root 2 pi, and I'll write this as minus infinity to infinity e to the power of, I'll expand this part, right? I'll expand this e to the power of minus half sigma squared. I'll take this out, and because this is tx, I'll take this as x minus mu whole squared. Because I'm taking overall sigma by 2 sigma squared outside, I'll even multiply this with 2 sigma t squared, right? So I can write it as 2 sigma squared tx. So this is the kind of numerator that is working out. Now I can very well complete the square, right? If you are looking at this part, okay, this is a minus here, so I have to put a minus out here. X minus mu whole squared, and I am getting 2 minus 2 sigma squared tx. I can very well write this as, if you try, this is a small adjustment that we have to do. I'll write this whole thing as x, the numerator part, everything remaining the same, right? E to the power of minus half. First thing is, if I'm having x minus mu whole square, this is one adjustment that you have to do. Minus 2 sigma squared tx. I will be able to write this as x minus of mu plus t sigma squared. Take it like this, x minus of mu plus t sigma squared whole square. If you are writing it this way, what is it? It is coming out x squared, right? Or probably you can very well x plus mu, x minus of mu plus t sigma squared whole square. So the you could very well see now this expansion can very well come out as, from here I can very well take out x squared, right? If you are expanding this, what is that? It is coming x squared minus 2 mu x plus mu squared minus 2 sigma squared tx. This is what we are getting in this expansion. Now when I write it like this, what is that I am getting? X squared plus, I am getting it as x squared plus, then this is mu squared plus t squared sigma power 4 plus 2 mu t sigma squared, 2 mu t sigma squared x. No, this is the square that I am getting, which is 2 mu squared plus t squared sigma power 4 plus 2 mu t sigma squared minus 2x into mu plus t sigma squared. This is what we are getting. So x squared term is already there. Then 2 mu x term is already there. Mu squared term is already there. And 2 sigma squared tx term is also already there. So these two terms are not there. So I will write this as this minus t squared sigma power 4 minus 2 mu t sigma squared. This is how I will write it. And during this process, I can very well take out e to the power of mu t plus half t squared sigma squared. I will take out, and the overall thing I'll put it as e sigma by root 2 pi integral minus infinity to infinity, again just completing the square, I'll write it as e to the power of minus half x minus of mu plus t sigma mu plus t sigma squared by sigma whole squared dx. Now you could very well see the whole thing internally x minus mu. This is the new mu, you can take it. So because that is the now that's a new mean of the distribution. So the parameter is becoming mu plus sigma squared t, and variance is becoming simple sigma. So I can very well take the moment generating function as e to the power of mu t plus half sigma squared t squared. So because I got the parameters to be mu plus t sigma squared and the variance I have got it as 0, I can very well get the moment generating function as mu t plus half sigma squared t squared. So this is the way I can generate the moment generating function associated with the normal distribution. But once I also have, let's say, moment generating function value of at t e power mu t plus half sigma squared t squared, I can differentiate it with respect to t. So which will be e power mu t plus half sigma squared t squared. Then I'll take the differentiation of this, which will give me mu plus half sigma squared into 2t. Now substituting t equal to 0, this whole thing will become 1, and this is mu plus again this will become 0. So that is where you will get the mean of this as 0. The same thing you can find out the second moment, expected value of x squared. So the same way again you have to differentiate this, find the expected value of x squared, then subtract the expected value of x whole squared, which is what will compute the mean for variance for us. So you can or you can directly say mean is mu and variance is sigma square. So that's how we use the normal distribution related stuff. Then we also talk about a standard normal distribution where mean is equal to 0 and sigma equal to 1. We call that as a standard normal distribution, right? For that particular distribution which has a mean equal to 0 and standard deviation equal to 1, we call it as a standard normal distribution. So it's as good as you said this is 0, this is 1, this is 1, which works out to 1 by root 2 pi e to the power of minus half x squared dx. And for this, you will get your probability distribution tables. You can very well use the tables to solve the problems associated with this normal distribution. You can see here, find the probabilities that a random variable having a standard normal distribution will take on less than 1.72. So it is like this. So this is a standard normal distribution. This is the mean of the distribution 0, right? This is 1 standard deviations, 2 standard deviations, 3 standard deviations. 1 standard deviation, 2 standard deviations, 3 standard deviations. Now when I am saying this value is less than 1.72, I am more interested in this entire area. What is this entire area? I can very well look at it in from the normal distribution tables which will be given, or I can very well use my spreadsheet as well to do the computation. So I can use a norms inverse function where or norms dist function, wherein I am taking the value of z 1.72. So this says almost 95.73% of the area, right? If I take the whole area under this curve to be around 100%, then below this 1.72 point, right? 1.72, the area under this curve is almost 95.72%. Similarly, so you can very well look up under the normal distribution tables and do the computation, but I am quickly here doing these kind of things from the Excel sheet itself. Less than minus 0.88, because this is 0 and this is minus 1, this should be minus 0.88. Less than, that means I am talking about this area. Now this one I can very well compute again using norms inverse. Sorry, I am talking about norms dist, wherein I am giving minus 0.88. So which gave me 18.94% is the area associated with this. Then I want to find out between 1.3 and 1.75. So 1.3 is somewhere here, 1.75 is somewhere here. So I will find out less than or equal to 1.3, how much is of the area. Less than 1.75, how much is the area. Subtract the two areas so that I can get between 1.3 and 1.75. So I'll do a norms dist, right? I'll do a norms dist wherein I am finding out for 1.3 says 90.32%, and the same function I am doing it for 1.75, it says 95.99. So the area under the normal distribution curve lesser than 1.3 is 0.90, whereas the area under the normal distribution curve less than 1.75 is 0.9599. So in between these two, if I want to find out, it's nothing but the subtraction of these two numbers, which is around 5.67%. So that's one more way. Similarly, I am talking about minus 0.25 to plus 0.45. The same logic I can use. So instead of 1.3, let me put minus 0.25. Right, this is the minus 0.25. Let me take plus 0.45. So the area under this, so this is 40.12%, this is 67.3%. The difference between the two is around 27.23%. So you can very well use the spreadsheet or even the normal distribution tables to compute the areas between these across all these various curves. So that's the kind of a comfort you really need to get. Alright. Now, the same logic, if I want to find the value of Z corresponding to a specific probability that falls between a listed values, I can use the inverse function. So I can find the value of Z corresponding to a specific probability. So it's like an inverse. So I'm looking for Z in the probability. I'm looking for the probability in that Z table. Based on that, I am saying for what values of the Z value that particular probability is coming out, which is what I would highlight as I would be highlighting as the corresponding Z value. Probably you look at it here with respect to the standard normal distribution table. Find the value of Z that corresponds to 0.3512. So what I can very well do is I'll use norms inverse function, wherein I am taking the probability of 0.3512. Whereas when you are doing it the table way, you will check for this 0.3512 under the table, under the probability, and based on that you will find out what is that particular value of Z which is corresponding to this probability. When I am using the spreadsheet, I am getting this as directly as minus 0.38, and the same thing that comes in, right, if I am looking at computing for 0.2533, I can very well find out for 0.232533 as an area. I can very well get it as minus 0.66. So either of the ways I can very well find out corresponding to the tables, right? Depending on the probability, I can very well mention what is the corresponding z value. Then one more important point that we need to look at in this context with normal distribution is, if X is having a normal distribution with a mean mu and a standard deviation sigma, then we can very well transform that by subtracting the mean, dividing by the standard deviation, then that particular distribution would be a standard normal distribution. So from every observation I subtract the mean, divided by the standard deviation, it would become a complete standard normal distribution. So for all kinds of practical purposes, if I have to do the solving of finding the probabilities of something, then this is what is the major application that we get in. We will convert everything from a normal distribution to a standard normal distribution, and based on that we would be computing the probabilities associated with that distribution. Suppose the amount of cosmic radiation to which a person is exposed when flying by jet across the United States is a random variable. Normal distribution, mean is 4.35 units. Standard deviation is 0.59 units. What is the probability that the person will be exposed to more than 5.2 units of cosmic radiation? So I want to find probability of X greater than 5.2. Now this is what we can do. Probability of X minus mu by sigma greater than 5.2 minus 4.35 divided by 0.59. So this is nothing but probability of Z greater than, what is this, 5.2 minus 4.35 divided by 0.59. 5.2 minus 4.35 divided by 0.59. So it's around 1.44. Probability of Z greater than 1.44. I can very well compute it. Now from this formula I'll use norms dist to identify probability of Z less than or equal to 1.44. And I'll subtract 1 minus of this to give me the probability of Z greater than 1.44. Z less than or equal to 1.44 is 1 minus 0.925. I'll do a 1 minus of this, saying around 7.48% chance that the radiation would be more than 5.2 units. So we have first computed the standard normal distribution from the normal distribution, and after that we have used the normal distribution table. So in this case the norms dist and the norms inverse functions are equivalent to the normal distribution tables itself. So we can use those tables for the computation purpose. What is the probability that a random variable having a normal distribution with a mean of 18.7 and a standard deviation of 9.1 will assume a value between 10.6 and 24.8, right? So both of them, probability, right, I can very well take that it is the probability of 10.6 less than or equal to X less than or equal to 24.8. The other way we can write it as 10.6 minus the mean is 18.7 divided by the standard deviation is 9.1 less than or equal to Z less than or equal to 24.8 minus 18.7 by 9.1. So the other side, what is that I am getting is 10.6 minus 18.7 divided by 9.1. So one side it is minus Z value should be greater than minus 0.89, and on the other side it is 24.8 minus 18.7 divided by 9.1. So it's around 0.67. So I can very well find out the norms dist, which is the area under the normal curve, standard normal curve associated with these Z values. So this is 18.67%, this is 74.86%. So I can very well, because I want the values between these two, I'll take the subtraction saying it's around almost 56.19% would be the result. So I can very well resort either to the tables or a software like Excel to really give me the result that I typically require. So that's how we can understand the normal distribution, a few important numericals associated with the normal distribution. Alright. Now let's move on to one more important topic here, where we are looking at the normal approximation to the binomial distribution. So many a cases, especially when the value of n is too large, in binomial distribution the probability of x equal to x is ncx p power x 1 minus p to the power n minus x, or theta power x 1 minus theta to the power n minus x. So that is what we have called as the binomial distribution probability distribution associated with this. And a few things, if n is too large, n is very large, and theta, which is the probability, very close to 0.5. Right? If you remember, n is large and theta is very small, and n theta is constant, we said binomial distribution will get approximated to a Poisson distribution. But on the other side, if n is large and theta is half 0.5, then we are saying binomial distribution can be approximated to a normal distribution. So if x is having a random variable, if x is a random variable with a binomial distribution, n and theta being the parameters of the binomial distribution, moment generating function of z equal to x minus n theta divided by n theta into 1 minus n theta, which is although nothing but, if you see here, x minus mu, mean of the binomial distribution is n theta, divided by the standard deviation of the binomial distribution is n theta into 1 minus theta under root. So this is nothing but x minus mu by sigma, right? So what we are saying is the moment generating function of this, it approaches a standard normal distribution when n tends to infinity. So we can very well try looking at this moment generating function. So initially I will go with the moment generating function of the binomial distribution. The moment generating function of the binomial distribution, I know I can take it as mx of t is 1 plus theta times e to the power of p minus 1 to the power n. This is what we have found out the moment generating function of the binomial distribution. Now I will take, instead of x, I'll take the moment generating function of x minus mu by sigma. Instead of x, I'll take it as moment generating function of x minus mu by sigma. So I can very well get it as e to the power of minus mu t by sigma, right? Because it's mu is the subtraction part of it, sigma is the division part of it. So I'll take the e to the power of minus mu t by sigma, and I'll take it as 1 plus theta times e to the power of p by sigma minus 1 to the power n. So this is what is coming out to be the moment generating function. So wherein I can very well take mu equal to n theta, and I can take the sigma value to be the square root of n theta into 1 minus theta. So based on that, I am taking a logarithm of this, log m x minus mu by sigma of t. So the e power will go off, which is coming out as minus mu t by sigma plus n times 1 plus theta into e to the power of t by sigma minus 1. right? So this I can get it as a logarithm. So this I will simplify it as minus mu t by sigma. So okay, I have taken the logarithm, so this becomes n log. So n log of this. So I will expand this n into logarithm of 1 plus theta to the power of this. 1 plus theta into e to the power of t by sigma. I'll expand it, right? So which will become 1 plus t by sigma plus t squared by sigma squared plus so on, t squared by 2 sigma squared t cube by t cube by 3 factorial sigma cube plus so on t power n by sigma power n factorial. And there is a minus 1 as well. So the minus 1 minus plus 1 is going to go off. So I am now expanding the log of 1 plus x, right? So this will become minus mu t by n, and because I am expanding it as log of 1 plus x, the log of 1 plus x, if you remember, it is x minus x squared by 2 plus x cubed by 3 minus so on. So log of 1 plus theta, I will take this, so which will come out as n theta times t by sigma, right, log of 1 plus some theta, which is coming out as t by sigma t squared, t by sigma squared times 1 by 2 t by sigma cube times 1 by 6. So t by sigma cube times 1 by 6 plus so on, minus I'll take again n theta squared by 2, again the same expansion, t by sigma, because this is for each one I am doing this. So it is becoming n theta squared times, because this is x minus x squared by 2 plus x squared by 3. So this is the x part. I am taking x squared by 2. Again t by sigma t squared by 2 sigma squared t cube by 3 factorial sigma cube and so on. Similarly, I can take it as n theta cube by 3, which is x cube by 3. Again the same t by sigma t squared by 2 sigma squared, because it's like some constant multiplied by theta. So that is where I am keeping all this constant out here. Now from here I will collect the powers of t. Now I could see here the power of t wise. So this is minus mu by sigma into t, and here I have n theta by sigma into t. So t wise it is becoming minus mu by sigma plus n theta by sigma. This whole thing is the t power. What about t squared? So this is not there. N theta by sigma square, right? And this is 2. N theta by 2 sigma squared minus here n theta squared by 2 sigma squared into t squared and so on. So this is what is coming out when I am collecting all the powers of t. So from here I can very well make out. So this is what is working out when I am substituting now in place of sigma. I'll put mu equal to n theta, and in place of sigma I'll take it as square root of n theta into 1 minus theta. So based on that I can very well simplify it, and once I simplify it I can very well take for r value greater than 2, the coefficient of t to the power of r is constant in terms of n by sigma to the power of r. So if when you are looking at n tending to infinite, this whole value is approaching 0. So the limiting value when n is tending to infinite, this whole value will work out to half t squared. So from here again, because this is the logarithmic value, I can very well take it back to the moment generating function when tending to infinite. I'll take it as e to the power of half t squared, which is the moment generating function when mu equal to 0 and sigma equal to 1. So which is what is the binomial distribution getting translated into a normal distribution with mean equal to 0 and sigma equal to 1. So this is where we could see the moment generating functions are equated, and what we could say is if the moment generating functions are equated, there is a one-to-one correspondence between the moment generating functions and the probability densities. So when the moment generating functions of two things are equal, even the probability densities can very well be equated. And there is one more important rule that we need to understand. If the moment generating function of one random variable approaches the moment generating function of other, then we can very well use that moment generating function to compare the probability densities as well. Probability density of the first random variable also will approach the probability density of the second random variable under the same limiting condition. So because of all these reasons, the binomial distribution can very well be approximated to a normal distribution, especially when n is very large and the theta value is close to 0.5. So use the normal approximation to a binomial distribution to determine the probability of getting 6 heads and 10 tails in 16 flips. So if I use the binomial distribution, the probability of getting 6 heads is 16c6 half to the power 6 half to the power 1 minus half to the power 16 minus 6. So the probability of getting 6 heads is 16c6. So I'll take the combination of 16 comma 6 into p to the power of 6, which is the theta to the power 6, multiplied by 1 minus theta, again 0.5 only, to the power 10. So if I am directly using the binomial distribution, I am getting the value as 0.12. Whereas now what is that it means? The probability of x equal to 6. Right? We are talking about probability of x equal to 6. So we will, because the point, for a point the probability does not exist in case of normal distribution, we will do a kind of a continuity correction. Right? So I will try to represent it as between anything that is lying between 6 minus half to 6 plus half. So this is what we typically call it as a continuity correction, because anything that is lying, because in case of normal distribution, it can't be one single value. We always talk about an interval. So anything that is lying between 5.5 to 6.5, we can round it off to 6. So we are doing a continuity correction here, very important point, especially when we are converting a binomial distribution into a normal distribution. So for each integer k, we will always replace it with the interval k minus half to k plus half. That is what is the continuity correction. If I am talking about an integer k, if I am converting it into a continuous case, I will take the interval k minus half to k plus half. So I will always look at the area under the curve associated with k minus half to k plus half, which is nothing but I'll look at the area between x equal to 5.5. So it means that I'm looking at probability that 5.5 is less than or equal to x less than or equal to 6. So, no, sorry, 6.5. So based on this, I can very well find out probability of 5.5 minus mean. What is the mean here? N theta. N is 16, theta is so n theta, which is the mean, which is 8, sigma. n theta into 1 minus theta is the variance. So 16 theta 1 minus theta. So the variance is 4. Standard deviation is 2. So probability of x minus mu by sigma less than or equal to z less than or equal to 6.5 minus 8 by 2. So which is otherwise working out as probability of minus 1 point. So this is 2.5 by 2, which is minus 1.25, and this is minus 1.5 by 2, which is minus 0.75. So we can very well find what is the probability that z lies between minus 1.25 to minus 0.75. So I'll use the norms test, find out for minus 1.25. Similarly, I'll use norms test to find out for minus 0.75. The difference between these two is the probability associated with lying between point plus or minus lying between 5.5 to 6.5, which works out to 12.09. And whereas when we have computed directly using the binomial distribution, it is 12.21. So you could clearly see, and here n is only 16, but if n goes even more larger, this even small gap also does not exist, it gets bridged down. So if n is getting larger and larger and probability of success is close to half, we can very well approximate the binomial distribution to a normal distribution. But the only thing we have to take care of when we are doing this kind of discrete distribution, approximating it to a continuous distribution, we have to just take that extra care that we need to do a continuity correction of that particular data. Continuity correction is nothing but whatever is the discrete value that we are taking, will create an interval out of it, generally minus half to plus half kind of an interval around that integer. So that's one more kind of understanding and the numerical evaluation that you really need to be comfortable with in this session. So this is where I want to end this session. We have dealt enough examples, enough conceptual part regarding the uniform distribution, the gamma distribution, the exponential, chi-squared, beta, normal distribution, and finally taking a normal approximation to the binomial distribution, where we have even considered the continuity correction as well. If you have any further queries regarding this session, you can very well get back to me by giving me a call on the number that I have provided below, or you can send in an email at vamsidhar@phasegurus.com. Thanks a lot for listening to this session. Thank you very much.